Welcome to Ask and Learn.
We'll be looking at virtual work. For this particular problem, I want to determine the spring stiffness as well as to determine the stability for equilibrium at sixth position, equilibrium position at theta equal to 60 degree. Okay, we have the spring here, and call this place point A. This is our point B and C. Right, this member AB and BC, they have the same length and the same weight. Let's call, which is this W. Okay, and we can establish that the datum at this point A, so to this point we have it to be, so let's call it the Y substitute 1, then to this other point, the center of gravity where this weight is acting. Let's call it Y subscript 2. Now, to solve the problem, we will determine the potential function and differentiate it with respect to theta to determine, plug in the value of theta to determine k, as well as take the second derivative of the potential function with respect to theta, and plug in our k, value of k and theta, to determine the stability. All right. Now, for the bars AB and BC, for each one of them, you're going to have for AB, sorry, you're going to have it to be equal to half times, because the weight will have through half of it, the length cos theta. So we have that. All right. So which is equal to 0.575 k cos theta. So we can just go to determine y2 is height. So it's going to give us what we have here, 0.75, as you can see from the diagram. 0.75 a cos theta plus, from this point up here we have the, from the center of gravity of w, uh, along the w along this BC, get up. So we're going to have it to be plus 1.5, because the length of each of the members AB and BC, and each one of them is 1.5 meters. We have that. All right, cos theta. Okay, so that if we sum this, it's going to give us 2.25 cos theta. Okay, all right. Now we can determine for the spring. For the spring, we have, let's call this. We are going to have it. Just call it x0. Considering the spring, the distance of twice. Normally, we are going to have it as if the spring is pulling, okay, through that entire that height. Okay, so we are going to have it to be s to be equal to 3 cos. Okay, 3 cos theta. That is 1.5 cos theta plus 1.5 cos theta. So we're going to give us 3 cos theta. Okay, then we can now consider the extension. Remember that the original length of the spring when on stretch is 1 meter. So let's say now our s, extension for the spring now is now this one, cos theta minus the original length, which is 1 meter, so that we have that. But we can decide to like take half of this spring then displacement. If we take half of this spring displacement or height, yes, half of it, we are going to have it to be equal to 1.5 cos theta. Okay, we are using this because I want to break the spring force there into the distance there into two. Okay, the spring force into two. Okay, so we are going to have this, all right, so that you can get what I'm trying to say now. The elastic potential E is equal to the same thing as uh, F over 2 S of S as the spring force times S, all right, still the same as equal to K, the spring constant as stiffness over 2 square this is still the same thing as saying is equal to half. Okay, the reason why I separated that the S into 2 divided it by 2 half uh, S over 2 squared is equal to K, sorry, plus, okay, so this continues plus K, so because of space I'm bringing this one here. Okay, so this was the reason why I separated. I decided to get S over 2. All right, so we have that. We can just plug everything now into equation. All right, our potential function will be V now equal V equal uh, the gravitational potential energy plus the elastic potential energy. So that for this now for V, we are going to have V to for VG. We said that this one has a negative uh, potential energy. Of course, we are given 8 IB. Okay, 8 IB. So 8 IB times 9.81. Okay, 9.81. Okay, times 0.75. Okay, cos theta that we got initially 0.75. Since we are looking at uh, W, sorry, W and y substitute 1. So we are into y substitute 1 now cos theta. So we have that. Okay. So that because since they are two, we have the W uh, y sub minus W y substitute theta minus W y substitute theta because this VG here, okay, VG is actually equal to minus W y substitute 1, okay, and minus W y substitute okay, minus wy substitute 1 minus wy substitute 2. Sorry, the two links. Okay, and minus w, sorry, w y substitute 1. Okay, for the two links a, b, and bc. All right, so we can just bring 2 here. So that we write in this again. Then bring in our spring. We're going to have it to be uh, k over 2 into 1.5 cos theta, okay, minus 0.5, okay. So we have that squared, and of course k is 2. Sorry, we remember we broke the spring force into 2 the other time, so we are going to have two of these ones, okay, again. So this is squared. Let's fix it squared. All right. So if we solve this now, if we differentiate that, you bring out everything and differentiate it, okay, we are going to have that for the equilibrium position. We are going to have the v, the theta, okay, the v, the theta to be equal to, uh, okay, again, have it to be equal to 235, 235 point, okay, 0.444 sine theta, okay, minus 9 sine theta, okay, cos theta, all right, k plus 3 sine theta, 3 sine theta k, and of course we equate it to 0 as we said for the equilibrium position. So plugging in theta to be 60 degree, will arrive at k to be equal to 156 point, okay, 0.9, okay, 6 Newton per meter. So if we plug in, if we take the second derivative of the second derivative, we are going to arrive at that is the squared v, the theta, okay, squared. We are going to arrive at that's for stability. We want to determine stability. We are going to arrive at 235, okay, 0.44, 0.44, okay, sine theta, all right, minus 4.5, 4.5 sine 2 theta, sine 2 theta, all right, k plus 2, 3, 3 sine theta k, okay, sine theta, 3 sine theta k, so that if we put in the value of k and theta, and let's see what we are going to have. If we do that, we are going to have the result is going to give us putting theta, we are going to have the square in value of theta and k as the spring, the constant of the spring, the stiffness of the spring rather. We are going to arrive at 1059.48, Okay, you can see that this is greater than zero. So for that position, okay, the equilibrium is stable one. So these are the values for the equilibrium position for K and the stability, right?